Each field of study has their own set of sacred works. You know what I'm talking about, is those papers and books which are so foundational that we base everything we teach and know in our discipline based on them. Some of us even have a little shrine in our office, and every time we walk by, we give it a respectful nod and maybe light a candle or two. In software engineering, this includes Extreme Programming by Beck, Gotta Have the Gang of Four, Constantine's Structural Program Design, Numerical Recipes in C, absolutely. Kern and Ritchie, C programming language, wait, signed by the author, oh yes. Gotta have clean code, and of course, don't forget elements of programming style. And of course, there's often a set of important papers, such as Dijkstra's go-to statements considered are harmful. And these kind of form the basis of our discipline. One of these papers is McCabe's 1976 paper about a complexity measure. I remember reading this when I was in college 35 years ago. Oh, I just revealed how old I was. Maybe I read it 35 years ago when I was 1. Yes. One day in class, I was going on about code understandability and how this impacts things like maintenance costs and defect rates. And a student asked Dr. Helfrich, what impacts code understandability? And of course, I referred to cyclomatic complexity, McCabe's paper back from 1976. And a student said, but Dr. Helfrich, you don't grade us on that. You grade us on variable names and comments. Well, I was stumped, of course. I said, well, let's talk after class. So after class, 2 students and I began a literature review to discover what factors impact code understandability. And we discovered 9 different metrics. It can be broadly categorized into 3 different categories: data flow complexity, code volume, and algorithmic complexity. And to our surprise, not a single empirical study has been done to verify these metrics. Not one. The closest we found were a collection of studies which related the various complexity measures to defect rates in existing code, but none directly measured understandability. There's a hole in the literature, so we decided to conduct this study ourselves. All right, there are several different measures. The first is span, and this is the average number of lines of code between usage of a variable. Basically, the further away the variable is between its declared and used, the larger the span value. Next is Choplin's Q. A variable used to control a loop or a conditional is 3 times more heavily weighted than a variable that is updated inside a loop, which is 2 times more heavily weighted than an input parameter or 1/2 for a constant variable. Next, we have cognitive complexity, and this relates to the basic control structures inside a nested block, the layers of nesting, and a linear block. Next, we have a chunk, and this is the use of a loop or an array versus an if statement or any change in control, which is going to be a +2. Cyclomatic complexity, imagine a flow chart, and the shape of the flow chart is G. The number of edges and the number of chunks are added together. The knot complexity, imagine we take code and we reduce it to a flow chart, and does any of the flowchart lines cross each other? That's going to be a knot. This usually happens, we have a return, a break, or a continue inside of a loop. And then Halstead, this relates to the number of occurrences of an operator, the number of occurrences of operands, the number of unique operators, and the number of unique operands. First, we created a function which took a single integer input parameter, a number between 1 and 100, and returned a single integer, a value between 1 and 5. And then we modify this function to exasperate or optimize on the various understandability metrics. Now keep in mind, these metrics are often interrelated. For an example, Choplin's Q measures, among other things, the number of variables used in a function, and increase the number of variables to increase Choplin's Q also tends to increase the number of source lines of code, which is a volume metric. Here's a couple examples of functions that were related by just a small number of parameters. In both cases, we have essentially the same algorithm, a bunch of if statements which return values, different numbers, of course. But notice how on the left-hand side, we have complex Boolean expressions. On the right-hand side, we have a more complex algorithm. And thus, the Halstead is going to be quite different on the left versus right, because on the left, the Boolean expression will be more complex. And then on the right, the cyclomatic complexity will be higher. But the knot count is going to be exactly the same because the shape of the algorithm is unchanged. Next, we have more complex math here. We have a for loop with a nested if statement. Observe how the span is going to be quite different between the two. However, the cyclomatic complexity will be exactly the same. Next, we have a range of values. Notice on the left-hand side, our knot complexity will be higher because we have a return statement that's nested inside an if or a for, so we break out of the loop. On the right, we do not.
However, our cognitive complexity to be exactly the same because the algorithm is unchanged. And then finally, we have two nested for loops and an if statement. Observe how my Chaplin's Q is going to be different, but my cyclomatic complexity can be the same, even though they perform essentially the same operation.
The experiment setup was to create a Qualtrics quiz with two versions of each question. The alternate forms were placed on opposite sides of the quiz to mitigate for test fatigue and for learning during the process of taking the quiz. The quiz was rolled out to university students as well as on various forums on LinkedIn. And after about 100 data points were collected, a preliminary analysis was conducted, and the results were inconclusive. To my surprise, there was basically no difference in time on task nor percentage of getting correct for any of the different question types. I was shocked, so I let the quiz ride for longer. Eventually, I had 368 individual test takes that were completed fully. And again, the tests were inconclusive. So let's take a look at our individual research questions.
All right, research question 1. Does the experience level of a programmer influence the time it takes for the programmer to predict the output of a code fragment? Okay, notice my p-value is 0.96. In other words, there's 96% chance what we're seeing is random. In other words, novice programmers and experienced programmers took a similar amount of time to complete each problem. This was a surprise. We thought that experienced programmers would do it quicker. Number 2, the experience level of a programmer influence the ability of the programmer to correctly predict the output of the code. Here my p is 0.38 times 10 to the negative 33. In other words, we're highly confident this is not random chance. However, after about year 4, in other words, by the time they get their bachelor's degree, their ability to correctly predict the output of code levels off. Does the various complexity metrics relate to the time it takes for a programmer to predict the output of a code fragment? And the answer is yes, my p is 1.71 times 10 to the negative 47. In other words, we're highly likely that what we're seeing is not random chance. However, and this is the crazy thing, the correlation is negative. In other words, the greater the complexity, the less time it takes for an individual to arrive at an answer. And this is true for all 7 complexity measures. And the final research question, do the various complexity measures relate to the ability of a programmer to correctly predict the output of a code fragment? And the answer is, well, we only reached statistical significance for 2, cyclomatic complexity and cognitive complexity. However, once again, this is exactly opposite what the theoretical framework suggests. In other words, programmers were able to predict the output of high complex items more than low complex algorithms.
So what's the main takeaway from this? The theoretical framework for software understandability is incomplete. Perhaps we should also do some studies on variable name meaningfulness and comment helpfulness. But as for the classic paper of a complexity measure, it doesn't stand up to empirical study.